Okay, we have integrated 2 1.2.4 notes. All of these notes are going to stem directly from the textbook. So none of these are going to be found in the framework notes that I posted on our agenda. So we're going to be describing a graph today, or taking situations and trying to figure out the graph that matches them. So a few things that we're going to address when we're describing a graph is this laundry list of things. So we've got shape, line of symmetry, asymptotes, intercepts, domain range, continuous or discrete, and whether it's a function or not. So I went through and just kind of mocked up some stuff on this very front page for you. Hopefully this looks familiar. So the shapes that you should be familiar with are linear, parabola, exponential, and then, kind of our catch-all, which we're just going to call curved for now. A main focus that we're going to be actually covering this year is the parabola. So I know that you guys experienced some of that a little bit in previous years. Well, this year it's a major focus. Line of symmetry itself is a line that looks like if you were to draw it into the picture, it would split your graph into two perfect halves. For example, like if you put a line down the middle of a parabola and you fold it over that line, the two sides of the parabola are going to match up, assuming that the parabola opens up or down. And then we've got asymptotes. You were introduced to asymptotes last year when you did exponential functions. It's the idea that a graph can get really close to something, but it doesn't actually get there. In future math classes, just as with everything else that you've learned in the past, you're going to learn in this class and you're going to learn in the future. There's always going to be a little bit more that you're going to learn about in future classes with this concept. Key thing to remember is that asymptotes are written as equations, just like lines of symmetry. And I went through and put down, okay, if you have a vertical asymptote or a vertical line of symmetry, it's always going to be x equals some number. Likewise, if you have a horizontal line of symmetry, like that horizontal line that we have there, it's identified as y equals. Okay, intercepts are locations on the x and the y axis. Just remember to write them as points. So an x-intercept is some number comma 0, and then a y-intercept is 0 comma some number. If you just say that the x-intercept is like 7, there are an infinite amount of locations on the graph that have just a 7 in them, so you got to be specific. Domain and range is going to be a little bit different this year. Depending on who you had in the past, you may or may not have learned some notation for domain and range. I know the main focus back in Integrated 1 was making sure that you knew how to describe it in words. This year, we're going to use symbols for that. So I went through and I wrote down, okay, if the graph is continuous, what kind of notation do you use? And we're going to do those on a couple of examples. And then if it's discrete, what do you use? Continuous, there's a big fancy definition for continuous when you are in calculus, but we're not there. We're a couple years off from that. So continuous at this point is if you drop your pencil on the paper, starting at the left-hand side of the graph, and you can trace the entire graph without lifting your pencil, it's continuous. If you have to pick your pencil up off the paper and then move it over to put it back onto the graph itself, it's discrete. And then a function, big thing that you guys did back in Integrated 1, which was, does it pass the vertical line test? So then if you draw a vertical line any point on the graph and you trace it all the way across the entire graph from left to right, you have to make sure that that line only hits the graph one spot at a time. If it hits it twice, then we're done. It's not a function anymore. So make sure that you guys have this stuff written down on the very front page. Okay, moving on. There's a resource page that I linked for you in today's agenda, and I went through and I picked out some of the specific graphs because I wanted to be able to talk about them. You're welcome to do graph A on your own. It's a linear function. Shouldn't be too bad. It's fairly straightforward. These are a little bit more interesting. So if we talk about graph B, let's go ahead and jump into that one first. Okay, I'm just going to go down the list of these things. So the first thing I'm going to identify here is what the shape is. Well, this shape doesn't really look like anything that you guys have done so far. It will in Integrated 3 next year. We may talk about it briefly this year, but not in great detail. So the shape of this, I would say, is just curved, only because my other option is that it's linear, and this is definitely not straight, so no. Line of symmetry. So I'm looking for some sort of invisible line that I can put on the graph so that when I fold the graph, the two halves of the graph match up perfectly. there isn't one here. It doesn't matter where I put a line, so there's no line of symmetry. So I would note that. So no line of symmetry. Then moving on to the next point, I would be talking about the asymptotes. Well, at this point, the only graphs that you have come into contact with that has asymptotes are the exponential graphs. So if you see a line, it doesn't have an asymptote. If you see a parabola, it does not have an asymptote. Actually, it's kind of a dead giveaway too, most of the time. If the graph is thorough and complete, you're going to see like a little dashed line on the graph somewhere. So it's a visual cue to you to know, oh, hey, yeah, you do have asymptotes. So this one is, there's no asymptotes either. So again, there's no invisible boundary that your graph is approaching but not actually crossing. Intercepts. Okay, we want to make sure that we specify between the x-intercepts and the y-intercept. But I think in this case, they're both the same. So yeah, it looks like the graph hits at 0, 0. So it is the only point on the coordinate plane, interestingly enough, that can be both an x-intercept and a y-intercept simultaneously. Just a little food for thought there. Next thing we want to talk about is the domain and range. Okay, so here's where the notation comes in. So referring back to the very first page, the first thing that I would actually want to do before I do domain and range is determine if it's discrete or continuous. So looking at the graph, if I start as far as I can on the left-hand side, so I'm going to go ahead and grab my red pen here. I start on the left-hand side where it is. Can I trace the entire graph without lifting my pencil? Yes, I absolutely can. So I would say that this graph here is going to be continuous. Based off of whether it is discrete or continuous is going to tell me what type of notation I'm going to need to use based off of if I use parentheses or brackets, or if I use braces, or if I use inequality symbols. It's ultimately up to you. So I'll tell you what both of them are here. Now, in the past, what I've done with domain and range, I think might be a little bit easier for some people, is I think about trying to if it's continuous, I think about boxing in the shape. So I'm going to go ahead and grab some vertical lines. I'm going to take a look at the graph. And remember, with domain and range, you always want to go from small to big. Domain is your x's typically, or your inputs. So we're going to start on the left-hand side, and we're going to try to go as far as we possibly can to the right-hand side. So figure out where this graph starts, if you want to think about it that way. So I know that this graph looks like it starts right at the y-axis. And then I want to go as far as I possibly can to the right-hand side and try to box it in. But if I go to the right of this, I see that there's an arrow, which means there's no boxing it in. If this thing is going off to the right, then that means that it is taking off as far to the right as I can possibly imagine. Well, the furthest thing to the right that I can imagine is infinity. So one of the ways to write this answer is using brackets or parentheses. So I know that the graph starts at 0. That's the furthest thing to the left. It's the smallest x value. It actually is located at that point. So I'm going to put a bracket on it. Now, if it was supposed to be a parenthesis and it was 0, you'd see an actual hole in the graph. It would look like a little dot that hasn't been filled in. It is continuous, so I can draw a comma, meaning the first number is where this thing starts. The second number is where this thing ends or terminates. Well, this thing doesn't. It keeps going on forever to the right, which is going to be positive infinity. Now, since infinity is just the notion that there are bigger numbers out there, it's not an actual number, I can't put brackets on it ever. I can never put brackets on infinity. I always have to put parentheses. I don't have an option. It couldn't be brackets. That's one way to write it. Another way to write it, so you don't have to do this both ways. You need to choose. These are x values, and your x values start at 0. So they're at 0, an equal to part, and they go to the right. They are bigger. So you could say x is greater than or equal to 0. They're technically the exact same answers, and I'm okay with either one of them. So go back to the graph. And now I want to box in my y's. So I want to find the lowest, remember it's always small to big, find the lowest possible point. Well, the lowest possible point looks like it's on the x-axis. But then if I try to box in the top of it as well, I still run into that arrow. Now I know it looks like the arrow is pointing to the right. It is, but it's also pointing up. So I have this, well, it looks like it goes as low as 0, and it hits at that point, so brackets. It is continuous all the way up as high as I can possibly imagine, parentheses. Now for range, you're still going to get greater than or equal to 0, but range are your y values. So make sure that you identify the correct variable here when you're talking about domain and range. And then the last thing that I need to do is determine if this thing is a function. So I'm going to go through, and normally what I would do if I'm trying to determine if something is a function and we were in class, I would take like a ruler or a pencil or something, just kind of drop it on the left-hand side of the graph. And so I'm going to use my orange line. So here's my vertical line or my pencil that I'd be dragging across. And I just keep dragging it across the graph. Okay, now I'm at the curve. You need to make sure that you only hit the curve one spot at a time. So if you look at all of those spots that I hit, I'm only ever hitting it once with each vertical line. If you're only hitting it once, then this thing is a function. If you hit it more than once, it's not a function. So yes, this is a function. Okay, now if we take a look at, and that covers the laundry list of things that we were supposed to do for part B. Part C is a lot like B. So now would be a great opportunity to go ahead and pause and see if you can figure out what our laundry list of items are. Okay, let's see how you did. So this shape is a parabola. We refer to it as a non-function parabola, but it's still a parabola. So like if you tilted it upright, it still has that kind of U shape to it. There is a line of symmetry. I went through and I highlighted it in green so that if I fold my graph on that green line, then the top half and the bottom half of the parabola would match up perfectly, like in sync 100%. So my line of symmetry is that green line. It is a horizontal line, which means it's going to be a y equals. It's just so happened to be at y equals 0. Parabolas don't have asymptotes. The x-intercept, there's only one of them here. It's -1, 0. The y-intercepts are 0, -1, and 0, 1. As soon as you see that there are two y-intercepts, it's a dead giveaway. This thing is not a function. Wow, why did I write that it was? Okay. So let's go ahead and change that down here at the bottom. This is definitely not a function. The graph is continuous. So I identified that it was continuous so it could help me out with what my domain and range was going to be. You will see that with my domain, I could lock it in on the left-hand side at -1, but then it takes off to the right forever. So my domain's going to be -1 to infinity. My range, though, I can't lock it in at all. Yes, I know that the arrows are pointing to the right, but if you take a look at them, the bottom one is also pointing down. It's not pointing down steeply, but it's still pointing down. So it's going from -infinity all the way up to +infinity. Another way that you could write that or say that is all real numbers. And that's what that capital R is with the two vertical bars. So hopefully we did okay on these. Let's move on. All right, D is definitely different. I want to make sure that we talk about this one. The shape itself. So if you were to connect the dots, not that we're going to, if you were to connect the dots though, this thing kind of looks like a curve. So I would say that the shape is curved. I don't know exactly what it is specifically, just curved. Okay, line of symmetry, I don't see one. So whenever you have that like a half a parabola curve or kind of looks like it's a twist or something, you're going to have a really hard time finding a line of symmetry if there is one. So I'm going to say no line of symmetry. Okay, moving on to the next one then. Asymptotes. Nope, no asymptotes. I don't see an invisible boundary that my graph is getting closer to. If it was exponential, maybe, but I'm not sure that it is. Intercepts. Okay, so the x-intercept itself. Looks like we've got a double counting one again. So we've got 0, 0 for both of them. So x-intercept and y-intercept are both 0, 0. Okay, I'm going to leave a spot for domain and range because I have to determine if it's discrete or continuous before I continue with that. So domain, range. All right, if I take a look at the graph and I put my pencil on the furthest point to the left, so it's 0, 0, can I mimic this graph by keeping my pencil on the paper the entire time? No, because it just looks like dots. So if that's the case, then this thing is definitely discrete because they're not connected. All right, that's going to change then how I determine domain and range. When your graph is discrete and they're just dots, so we're going to talk about some crazy looking ones here later too, but just dots. All you're going to do is identify the x values of them for the domain. So you're going to make a list. So we're going to use the curly braces for this, not parentheses or brackets, and then we're going to go through and we're going to identify the x values. And I like to go from left to right or small to big. So the first x value for the point is 0. The next x value is 1. So see, I'm just listing them off. And then 2 and then 3. So put commas in between them, and you have to exhaust the list. You got to write out the whole thing. Okay, range is going to be the exact same idea. So with range, I know that this is discrete also, so I'm going to go ahead and do my curly brackets, but these are your y values this time. I remember that we had a point at 0, 0, so I definitely have a y value of 0. And then now you're just going to take a look at the y values. Normally we go from small to big, so kind of a good habit to get into. It looks like we have a 1, then a 4, and then a 9. So I would do 0, 1, 4, 9, all separated by commas. So whenever you just have dots, so no funny business, just a dot. This is how we identify the domain and the range. We did say that it was discrete and then whether or not it's a function. If I went through and I drew vertical lines through each one of those points, I'm only hitting one point at a time. So this thing is going to definitely be a function. So a little bit different with the domain and range on that one. Okay, E is a lot like what we had done previously. I am going to pause and go ahead and fill it in, but here's my recommendation to you to just be careful on. With domain and range, it is always, always, always small to big. So domain is left to right. Range is bottom to top. So keep that in mind while you do this problem. Okay, go ahead and take a minute and double check and make sure we got the same thing. It is a parabola. I did try to color code throughout. So we've got the line of symmetry at x equals 0, parabola, so there's no asymptotes. There are 2 x-intercepts this time, which is kind of what we expect most of the time on parabolas like this. A single y-intercept. The domain this time, yes, I realize that it looks like it's pointing down, but we really need to focus on the fact that domain is left to right. And it's still continuing out further to the left and further to the right. Notice the red arrows. I know they look like they're pointing down, but they're also pointing out as well. The range, this was the one that I was trying to warn you about at the very beginning of this question. You always want to go from small to big. So if you take a look at the graph, we have the blue arrows pointing down, which means this thing is going down as low as we can possibly imagine, which is going to be negative infinity. It's the smallest possible number we know, or concept of number that we know. And then it goes up and it stops at 8. So you can use the parenthesis negative infinity comma 8 bracket, or you can do y is less than or equal to 8. And then I knew to use that notation because it was continuous. And then yes, this is definitely a function. Okay, so now we're on to H and J. And I believe with H and J, you have enough information at this point to determine and be able to do the problems yourself. So I am going to go through and I'm going to fill both of them out. So again, you're going to want to pause, or at least I would, just make sure that you can do this. Pause. Do both of them. If you get stuck on something, put a little mark next to it so you know which ones you're struggling with. And then when you're ready to double check, go ahead and push play again, and let's just see if we match. Okay, this is a great opportunity to pause it again before I move on to the next slide, and then check and see how you did on this. Hopefully it's getting easier as we go. Okay, on to the last one. I chose graph L because it doesn't have any arrows on it, so there's no infinity aspect to this. So the only thing I think we have to be a little bit more careful about is domain and range. But in this case, there is a clear beginning and a clear ending for domain, likewise for range. So take this opportunity to pause and then check and see if we match. Okay, so here's graph L now. It kind of looks like a half circle to me, so I went through and said that, but you can just say that it's curved. And then I've got my line of symmetry. I did try to color code all of my graph, and then just take a look and see if you match. You'll notice the big difference with the domain and range here. There was a clear beginning and a clear ending to this graph. I didn't have any arrows. So I used brackets on both ends. And then if I wanted to write this out for my range, so if I do my range, that would be 0, 8, y is in between. And whenever you have like a section in between, then your variable is trapped in between them and the inequality is open to the right hand side. So if we do your domain, this would have been -8 on the left-hand side, +8 on the right-hand side. X is the variable, opening to the right. Okay, moving on to our next slide, we're now actually going to take a look at some specific problems from the book. Okay, so moving on to 1-59, now we've got some scenarios and we've got some pictures, and our job is to just match them up. So if we have so go ahead and take a moment, make sure you read A, B, and C, take a look at the 3 pictures, and then we need to label the axes appropriately as well. So we just match the scenarios, write a brief description. So at this point, I'm going to go ahead and match the scenarios, and then I would recommend that you go through and put a little bit more detail on each one of these graphs for yourself. So price of a postage stamp over 20 years. So I want to think about whether or not that would be discrete or whether it would be continuous. Okay, so if I think of a postage stamp, continuous would be that a postage stamp would go from like 39 cents to 39.00001 cent, 39.0001 cent, 39.001 cent, 39.01 cent, 39.1 cent, 39.0 cent, or 39.2 cent, and so on and so forth. So I'd have all these fractions of decimals and everything. I don't think that's the case. So I'm pretty sure that A is going to go with the only discrete graph up here, which is 3. So I'm going to match those two guys together. Definitely going to say that A goes with 3. So I'll put my A there. And then come back, make sure that you label your axes that go with this. So I know that it's discrete. I also know that the cost of postage stamps has gone up over the years. So I'm going to say that this is discrete. Definitely want to say that it is increasing because the cost is going up over time. It is a function. I know it's kind of hard to see if it is or not, kind of right at the edges, but it is. You're not going to go in and get a single stamp that is both 39 cents and 40 cents at the same time. It's a 39-cent stamp or a 40-cent stamp. You can't have that stamp count double. So I'm definitely going to say that this is a function. You can even put your vertical lines on there and see that it is. And then you can go ahead and put the time frames on here yourself. So maybe this could be like time in years. And then the vertical axis could be like cents. And then you can go and put some increments on there. Okay, so that takes care of A. So A's handled. All right, let's take a look at B. The number of hours of daylight each day over a year. Okay, number of hours of daylight. That's continuous because we're going to have like more hours and then like fractions of hours or pieces of hours. And then we can go from decimals or minutes, seconds, however you want to take a look at it. So I do believe that this is going to be continuous. And the numbers of hours daylights over a year. All right, if we think about January, the days are shorter. The daylight days are shorter in the winter and in the fall. So if we think about January's still in the winter. So we're not going to have as many daylight hours. Then over the summer, the days seemingly get longer, but that's because you have more daylight during those times. So if I took a look at the two that I have remaining, I'm going to say that B is the first one because it shows that I don't have, so it's lower. So I have less daylight hours, then it looks like it kind of creeps up. So this would kind of be like summer right in there. And then once fall hits, and then down to winter. So we start like losing our daylight hours again. So I would say that this one is B. Okay, so I know that it is continuous. I'm not going to talk about whether it's increasing or decreasing. I mean, you can talk about it going up and then going down. So increasing, then decreasing. And then, I don't know. I mean, you would say that the days, so let's say we could even do like months down here. So it could be like January in the beginning, and then February, and then March, and then April, so on and so forth. You can do it in terms of quarters also. So maybe it's the first quarter of the year that is before we transition into spring. And then the second quarter of the year is us transitioning into summer, so on and so forth. And then up here on the vertical axis, we could put like hours. I think would probably make the most sense. So how many hours of daylight time are we actually going to be having? Okay, so then by default, that means that C is going to be 2, which honestly, to me, this is the dead giveaway. So most of the time, whenever you purchase a car, and I'm not including like any of the classics. So if you buy like a classic car, so the cost of those in the beginning wasn't a huge amount, but now over time they have gained value. Most cars, though, when you purchase them, as soon as you drive off the lot, your car just starts losing value. And then hopefully it tapers off at one point, assuming you don't get into any type of an accident. So I would say that, yeah, C is definitely this one. So I'd say this is continuous. It's definitely decreasing over time, unfortunately, but true. It is a function. Oh, we would have said that on the first graph also, that it was a function. And then if we wanted to go back to the second one and put some labels on this, so where C was, then we would say, I don't know, this could be like time, so years since purchase. And then on the vertical axis, we could put value, so money. So then we were able to handle A and B and C. Okay, let's take a look at 1-60, and this is going to be the last one that we do. So, and this one is fairly straightforward, I believe. So take a look at the question, and we have these 4 graphs, and basically Frank has given these very succinct descriptions, and we have to determine if this is enough to figure out which one is which. So Frank goes ahead and says the graph is discrete. I've got 4 options. Well, I can tell you right now that 2 of these are discrete, but I don't know which one he's talking about. So with the discrete graph, I'm going to say that this is the very first option, or, well, and technically. And the other one that's discrete is 3. So I currently don't have enough information to determine which graph he's even talking about. Linear and increasing. Okay, so linear, straight. Increasing, so as we come in from the left, so if we read left to right, it looks like the graph is going up. Well, there's 2 of them. That's 1 or 2. They both fit the bill. So I'm a little hesitant right now for Frank to get full credit on something like this because his description isn't thorough enough. Non-linear, okay, so curved, decreasing. That means that the graph looks like it's going down from left to right. Okay, that looks like 3 and 4. So ultimately, if Frank was in my class and he gave me these descriptions, I would write these notes off to the side and be like, dude, I don't know which one you're talking about. So you got to be a little bit more clear. And I think that brings our notes to a conclusion for this unit, or excuse me, for this section.